Here are solutions to homework set number 10 for ECE 376 Embedded Systems. This homework set looks at timer 1 capture, timer 1 compare interrupts, and a PIC 18F4620 microcontroller. So the goal here is to use an ultrasonic range sensor to determine the range to an object, like is there a cat on the table, and if a cat appears, the alarm goes off. So here's what it should look like. So here I've got the PIC controller along with the range sensor, a speaker, and an H bridge. When a cat comes by, it's supposed to set up an alarm, tell the cat to get off the table. And it actually works better if you have a nice flat object, like a box. I can see the distance to the box. That's the first number, distance in millimeters. As the box moves away, at 250 millimeters, the alarm turns off. At 200 millimeters, the alarm turns on. So that's the cat off the table. So how do we do that? Well, the first step is to find yourself a cat. And here I got from Amazon. This is a cat that looks kind of like Momo, my old buddy kitty cat. Second thing we need is a range sensor, a speaker, a PIC microcontroller. What the code looks like is I've got actually 4 different interrupt service routines running. Timer 0 is outputting a pulse every 100,000 clocks. So this has a prescaler of 8. N is 100,000. So the frequency is 5 million over 2 times n, which is 25 hertz. So that's the square wave that's going to the range sensor. This is going to the trigger input. Set with timer 0. Timer 1 just keeps track of time, not really used for anything else. Timer 2 is the frequency, actually divided by 8 to give you a nice, annoying 22 hertz square wave. Capture 1 is the pulse width. With the range sensor, the pulse width is distance. I'm going to capture the rising edge and the falling edge. So this is capture 1. If I just saw the rising edge, now look for falling edge. If I just saw the falling edge, now look for rising edge. On the rising edge, I save the time as time 0. Falling edge, I save the time as time 1. Take the difference in time, that's dt. The main loop then converts distance to millimeters. If I'm more than 250 millimeters, turn off the alarm. Less than 200, turn on the alarm. And the alarm shows up over here in timer 2. If the alarm is turned on, turn on RC3, otherwise turn off. So here's kind of what it looks like. So this is showing off the distance in millimeters to an object, the alarm. If I take a box, it likes boxes. Move the box away, that's the distance to the box in millimeters. Fairly clean. Move the box closer in, distance drops. And then where it turns on should be 250. Actually, turns on at 200. But there it turns on at 200. Stays on until it gets to 250 millimeters. And that way, if a cat comes around and winds up on the table, here's my cat. The alarm should go off. Tell the cat to get off the table. Now, in terms of validation, what I'm looking for in validation is to collect data. For example, in this case, I can take a ruler, measure distance to a metal box, and see if the box distance, measure distance, matches up with the rain sensor. So as I move the box back and forth, I'm getting the distance based upon a millimeter ruler, distance based upon the rain sensor. Match it pretty well. I can check to see where the alarm turns on and off. Move the box forward and back. See the on-off distance. Measure the frequency. And with that, I've got a off-the-cat embedded system using a PIC microcontroller along with a whole bunch of interrupts, timer 1 capture, timer 0, timer 2, with a PIC microcontroller. Homework set number 10.